fit one cycle, some number of epochs, I often pick 4, and some learning rate, which defaults to 3e neg 3. I'll just type it out fully so you can see. And then we do that for a bit, and then we unfreeze it, right? And then we learn some more. And so this is the bit where I just take whatever I did last time and divide it by 10. And then I also write like that, and then I have to put one more number in here, and that's the number that I get from the learning rate finder, the bit where it's got the strongest slope. So that's kind of the don't have to think about it, don't really have to know what's going on, rule of thumb that works most of the time. But let's now dig in and actually understand it more completely. So we're going to create this mathematical function that takes the numbers that represent the pixels and spits out probabilities for each possible class. And by the way, a lot of the stuff that we're using here, we are stealing from other people who are awesome, and so we are putting their details here. So like, please check out their work, because they've got great work that we are highlighting in our course. I really like this idea of this little animated GIF of the numbers. So thank you to Adam Geitke for creating that. And I guess that was probably on Quora by the looks of this Medium. Oh yes, it was too, that terrific Medium post, I remember. In fact, a whole series of Medium posts. So, so let's look and see how we create one of these functions. And let's start with the simplest function I know, y equals ax plus b. Okay, that's a line, right? That's a line, and the gradient of the line is here, and the intercept of the line is here. Okay, so hopefully, when we said that you need to know high school math to do this course, these are the things we're assuming that you remember. If we do kind of mention some math thing, which I'm assuming you remember, and you don't remember it, don't freak out, right? Happens to all of us. Khan Academy is actually terrific. It's not just for school kids. Go to Khan Academy, find the concept that you need a refresher on, and he explains things really well. So strongly recommend checking that out. You know, remember, I'm just a philosophy student, right? So I, all the time, I'm trying to either remind myself about something or I never learnt something, and so we have the whole internet to teach us these things. So I'm going to rewrite this slightly. Y equals a1x plus a2. So let's just replace b with a2. I'm just going to give it a different name. Okay. So there's another way of saying the same thing. And then another way of saying that would be if I could multiply a2 by the number 1. Okay, this still is the same thing. Okay. And so now at this point, I'm actually going to say, let's not put the number 1 there, but let's put an x1 here and an x2 here, and I'll say x2 equals 1. Okay, so far, this is not, you know, this is pretty early high school math. This is multiplying by 1, which I think we can handle. Okay, so these two are equivalent with a bit of renaming. Now, in machine learning, we don't just have one equation, we've got lots, right? So if we've got some data that represents the temperature versus the number of ice creams sold, then we kind of have lots of dots. And so each one of those dots, we might hypothesize, you know, is based on this formula, y equals a1 x1 plus a2 x2, right? And so basically there's lots of, so this is our y, this is our x. There's lots of values of y, so we can stick a little I here. And there's lots of values of x, so we can stick a little x here. Okay? So the way we kind of do that is a lot like NumPy indexing, right? But rather than things in square brackets, or PyTorch indexing, rather than things in square brackets, we kind of put them down here in our kind of in a subscript to our equation. Okay, so this is now saying there's actually lots of these different yi's based on lots of different xi1 and xi2. Okay, but notice there's still only one of each of these. Right? So these things here are called the coefficients or the parameters. So this is our linear equation, and this is still, we're going to say that every xi2 is equal to 1. Okay. Why did I do it that way? Because I want to do linear algebra. Why do I want to do linear algebra? Well, one reason is because Rachel teaches the world's best linear algebra course. So if you're interested, check out Computational Linear Algebra for Coders. So it's a good opportunity for me to throw in a pitch for this free course, for which we make no money, but never mind. But more to the point right now, it's going to make life much easier, right? Because I hate writing loops. I hate writing code, right? I just want the computer to do everything for me. And anytime you see like these little I subscripts, that sounds like you're going to have to do loops and all kinds of stuff. But what you might remember from school is that when you've got like two things being multiplied together, and then they get added up, that's called a dot product. And then if you do that for lots and lots of different numbers I, then that's called a matrix product. So in fact, this whole thing can be written like this. Rather than lots of different yi's, we can say there's one vector called y, which is equal to one matrix called x times one vector called a. Now at this point, I know a lot of you don't remember that. So that's fine. We have a picture to show you. I don't know who created this. Oh, now I do. Somebody called Andre Stouts created this fantastic thing called matrix multiplication.xyz. And here we have a matrix by a vector. And we're going to do a matrix vector product. Go. That times that times that plus 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 plus. That times that times that plus 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 plus. That times that times that plus 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 plus. Finished. That is what matrix vector multiplication does. In other words, it's just that, except his version is much less messy. Okay, so let's, this is actually an excellent spot to have a little break and find out what questions we have coming through our students. What are they asking, Rachel? Next.
Okay. When generating new image data sets, how do you know how many images are enough? What are ways to measure enough?
Yeah, that's a great question. So another possible problem you have is you don't have enough data. How do you know if you don't have enough data? Because you found a good learning rate, because if you make it higher, then it goes off into massive losses. If you make it lower, it goes really slowly. So you've got a good learning rate. And then you train for such a long time that your error starts getting worse. Okay, so you know that you've trained for long enough. And you're still not happy with the accuracy. It's not good enough for the, teddy bear cuddling level of safety you want. So if that happens, there's a number of things you can do, and we'll learn about some of them we'll learn pretty much all of them during this course. But one of the easiest ones is get more data. Okay, if you get more data, then you can train for longer, get a higher accuracy, lower error rate without overfitting. Unfortunately, there's no shortcut. I wish there was. I wish there was some way to know ahead of time how much data you need. But I will say this, most of the time you need less data than you think. So organizations very commonly spend too much time gathering data, getting more data than it turned out they actually needed. So get a small amount first and see how you go.
What do you do if you have unbalanced classes, such as 200 grizzlies and 50 teddies?
Nothing. Try it. It works. A lot of people ask this question about how do I deal with unbalanced data. I've done lots of analysis with unbalanced data over the last couple of years, and I just can't make it not work. It always works. So there's actually a paper that said, like, if you want to get it slightly better, then the best thing to do is to take that uncommon class and just make a few copies of it. That's called oversampling. But like, I haven't found a situation in practice where I needed to do that. I've found it always just works fine for me.
Once you unfreeze and retrain with one cycle again, if your training loss is still lower than your validation loss, likely underfitting, do you retrain it unfrozen again, which will technically be more than one cycle, or do you redo everything with a longer epoch per the cycle?
Hey, you guys asked me that last week. My answer's still the same. I don't know. Either's fine. If you do another cycle, then it'll kind of maybe generalize a little bit better. If you start again, do twice as long, it's kind of annoying. Depends how patient you are. It won't make much difference. You know, for me personally, I normally just train a few more cycles. Yeah, it doesn't make much difference most of the time.
So showing the code sample where you were creating a CNN with ResNet 34 for the Grizzly Teddy classifier. It says this requires ResNet 34, which I find surprising. I had assumed that the model created by .save, which is about 85 megabytes on disk, would be able to run without also needing a copy of ResNet 34.
Yeah, and I understand. We're going to be learning all about this shortly. You don't. There's no copy of ResNet 34. ResNet 34 is actually what we call an architecture. We're going to be learning a lot about this. It's a functional form. Just like this is a linear functional form. It doesn't take up any room. It doesn't contain anything. It's just a function. ResNet 34 is just a function. It doesn't contain anything. It doesn't store anything. I think the confusion here is that we often use a pre-trained neural net that's been learnt on ImageNet. In this case, we don't need to use a pre-trained neural net. And actually, to entirely avoid that even getting created, you can actually pass pre-trained equals false, and that'll ensure that nothing even gets loaded, which will save you another 0.2 seconds, I guess. So yeah, but we'll be learning a lot more about this. So don't worry if this is a bit unclear. But the basic idea is this thing here is basically the equivalent of saying, is it a line, or is it a quadratic, or is it a reciprocal? This is just a function. This is the ResNet 34 function. It's a mathematical function. It has no, doesn't take any storage. It doesn't have any numbers. It doesn't have to be loaded. As opposed to a pre-trained model. And so that's why when we did it at inference time, the thing that took space is this bit, which is where we load our parameters. Which is basically saying, as we're about to find out, what are the values of A and B. We have to store those numbers. But for ResNet 34, you don't just store two numbers, you store a few million, or a few tens of millions of numbers. So why did we do all this? Well, it's because I wanted to be able to write it out like this. And the nice thing of being able to write it out like this is that we can now do that in PyTorch with no loops, single line of code, and it's also going to run faster. PyTorch really doesn't like loops, right? It really wants you to send it a whole equation to do all at once, which means you really want to try and specify things in these kind of linear algebra ways. So let's go and take a look, because what we're going to try and do then is we're going to try and take this, we're going to call it an architecture, right? It's just like the world's tiniest neural network. It's got two parameters, you know, A1 and A2. We're going to try and fit this architecture to some data. So let's jump into a notebook and generate some dots, right? And see if we can get it to fit a line somehow. And the somehow is going to be using something called SGD. What is SGD? Well, there's two types of SGD. The first one is where I said in lesson 1, hey, you should all try building these models and try and come up with something cool. And you guys all experimented and found really good stuff. So that's where the S would be student. That would be student gradient descent. So that's version 1 of SGD. Version 2 of SGD, which is what we're going to talk about today, is where we're going to have a computer try lots of things and try and come up with a really good function, and that will be called stochastic gradient descent. The other one that you hear a lot in the on Twitter is stochastic grad student descent. So that's the other one that you hear. So we're going to jump into lesson 2 SGD. And so we're going to kind of go bottom up rather than top down. We're going to create the simplest possible model we can, which is going to be a linear model. And the first thing that we need is we need some data. And so we're going to generate some data. The data we're going to generate looks like this. So this might represent temperature, and this might represent number of ice creams we sell, or something like that. But we're just going to create some synthetic data that we know is following a line. And so as we build this, we're actually going to learn a little bit about PyTorch as well. So basically the way we're going to generate this data is by creating some coefficients. A1 will be 3, and A2 will be 2. And we're going to create some, like we looked at before, basically a column of numbers for our x's and a whole bunch of 1s. And then we're going to do this, x at a. What is x at a? X at a in Python means a matrix product between x and a. It actually is even more general than that. It can be a vector-vector product, a matrix-vector product, a vector-matrix product, or a matrix-matrix product. And then actually in PyTorch specifically, it can mean even more general things where we get into higher rank tensors, which we will learn all about very soon. Right? But this is basically the key thing that's going to go on in all of our deep learning. The vast majority of the time, our computers are going to be basically doing this, multiplying numbers together and adding them up, which is a surprisingly useful thing to do. Okay, so we basically are going to generate some data by creating a line, and then we're going to add some random numbers to it. But let's go back and see how we created x and a. So I mentioned that we've basically got these two coefficients, 3 and 2, and you'll see that we've wrapped it in this function called tensor. You might have heard this word tensor before. Who's heard the word tensor before? About 2/3 of you. Okay, so it's one of these words that sounds scary, and apparently if you're a physicist, it actually is scary. But in the world of deep learning, it's actually not scary at all. Tensor means array. Okay, it means array. Now specifically, it's an array of a regular shape, right? So it's not an array where row 1 has 2 things and row 3 has 3 things and row 4 has 1 thing, what you call a jagged array. That's not a tensor. A tensor is any array which has a rectangular or cube or whatever, a shape where every element, every row is the same length, and then every column is the same length. So 4 by 3 matrix would be a tensor. A vector of length 4 would be a tensor. A 3D array of length 3 by 4 by 6 would be a tensor. That's all a tensor is. Okay, and so we have these all the time. For example, an image is a 3-dimensional tensor. It's got number of rows by number of columns by number of channels, normally red, green, blue. So for example, kind of a VGA picture would be 640 by 480 by 3. Or actually, we do things backwards. So when people talk about images, they normally go width by height. But when we talk mathematically, we always go number of rows by number of columns. So it would actually be 480 by 640 by 3. And that will catch you out. We don't say dimensions, though, with tensors. We use one of two words. We either say rank or axes. Rank specifically means how many axes are there, how many dimensions are there. So an image is generally a rank 3 tensor. So what we've created here is a rank 1 tensor, or also known as a vector, right? But like in math, people come up with slightly different words, or actually no, they come up with very different words for slightly different concepts. Why is a one-dimensional array a vector, and a two-dimensional array is a matrix, and then a three-dimensional array, does that even have a name? Not really. Doesn't have a name. Like, it doesn't make any sense. Whereas with computers, we try to have some simple, consistent naming conventions. They're all called tensors. Rank 1 tensor, rank 2 tensor, rank 3 tensor. You can certainly have a rank 4 tensor. If you've got 64 images, then that would be a rank 4 tensor of 64 by 480 by 640 by 3, for example. So tensors are very simple. They just mean arrays. And so in PyTorch, you say tensor, and you pass in some numbers, and you get back, in this case, just a list, get back a vector. Okay? So this then represents our coefficients, the slope and the intercept of our line. And so, because remember, we're not actually going to have a special case of ax plus b. Instead, we're going to say there's always this second x value, which is always 1. You can see it here, always 1, which allows us just to do a simple matrix vector product. Okay, so that's A. And then we wanted to generate this X array of data, which is going to have, we're just going to put random numbers in the first column and a whole bunch of 1s in the second column. So to do that, we basically say to PyTorch, create a rank 2 tensor. Actually, no, sorry, let's start that again. We say to PyTorch that we want to create a tensor of n by 2. So since we passed in a total of 2 things, we get a rank 2 tensor. The number of rows will be n, and the number of columns will be 2. And in there, every single thing in it will be a 1. That's what torch.ones means. And then, this is really important, you can index into that, just like you can index into a list in Python, but you can put a colon anywhere. And a colon means every single value on that axis, or every single value on that dimension. So this here means every single row. And then this here means column 0. So this is every row of column 0. I want you to grab a uniform random number. And here's another very important concept. In PyTorch, anytime you've got a function that ends in an underscore, it means don't return to me that uniform random number, but replace whatever this is being called on with the result of this function. So this takes column 0 and replaces it with a uniform random number between -1 and 1. So there's a lot to unpack there, right? But the good news is those 2 lines of code, plus this one, which we're coming to, cover 95% of what you need to know about PyTorch. How to create an array, how to change things in an array, and how to do matrix operations on an array. Okay, so there's a lot to unpack, but these small number of concepts are incredibly powerful. So I can now print out the first 5 rows. Okay, so colon 5 is standard Python slicing syntax to say the first 5 rows. So here are the first 5 rows, 2 columns looking like my random numbers and my 1s. So now I can do a matrix product of that X by my A, add in some random numbers to add a bit of noise, and then I can do a scatter plot. And I'm not really interested in my scatter plot in this column of 1s, right? They're just there to make my linear function more convenient. So I'm just going to plot my 0 index column against my Ys, and there it is. PLT is what we universally use to refer to the plotting library matplotlib. And that's what most people use for most of their plotting in Python. In scientific Python, we use matplotlib. It's certainly a library you'll want to get familiar with because being able to plot things is really important. There are lots of other plotting packages. Lots of them, the other packages are better at certain things than matplotlib, but like matplotlib can do everything reasonably well. Sometimes it's a little awkward, but you know, for me, I do pretty much everything in matplotlib because there's really nothing it can't do, even though some libraries can do other things a little bit better or a little bit prettier. But it's really powerful, so once you know matplotlib, you can do everything. So here I'm asking matplotlib to give me a scatter plot of my x's against my y's, and there it is. Okay, so this is my my dummy data representing, like, you know, temperature and ice cream sales. So now what we're going to do is we're going to pretend we were given this data and we don't know that the values of our coefficients are 3 and 2. So we're going to pretend that we never knew that. We have to figure them out. Okay, so how would we figure them out? How would we draw a line to fit to this data? And why would that even be interesting? Well, we're going to look at more about why it's interesting in just a moment, but the basic idea is this. If we can find, this is going to be kind of perhaps really surprising, but if we can find a way to find those two parameters to fit that line to those, how many points were there? N was 100. If we can find a way to fit that line to those 100 points, we can also fit these arbitrary functions that convert from pixel values to probabilities. It'll turn out that this techniques that we're going to learn to find these two numbers works equally well for the 50 million numbers in ResNet 34. So we're actually going to use an almost identical approach. So that's this, and this is the bit that I found in previous classes people have the most trouble digesting. Like I often find, even after week 4 or week 5, people will come up to me and say, I don't get it. How do we actually train these models? And I'll say, it's SGD. It's that thing we saw in the notebook with the two numbers. It's like, yeah, but we're fitting a neural network. It's like, I know, and we can't print the 50 million numbers anymore, but it is literally identically doing the same thing. And the reason this is hard to digest is that the human brain has a lot of trouble conceptualizing of what an equation with 50 million numbers looks like and can do. So you just kind of, for now, will have to take my word for it. It can do things like recognize teddy bears. You know, these functions turn out to be very powerful. And we're going to learn a little bit more in just a moment about how to make them extra powerful. But for now, this thing we're going to learn to fit these two numbers is the same thing that we've just been using to fit 50 million numbers. Okay, so we want to find what PyTorch calls parameters, or in statistics you'll often hear called coefficients, these values of A1 and A2. We want to find these parameters such that the line that they create minimizes the error between that line and the points. So in other words, you know, if we created, you know, if the A1 and A2 we came up with resulted in this line, then we'd look and we'd see like how far away is that line from each point. And we'd say, oh, that's quite a long way. And so maybe there was some other A1 or A2 which resulted in this line. And then we'd say like, oh, how far away is each of those points? And then eventually we come up with, we come up with this line, and it's like, oh, in this case, each of those is actually very close. Right? So you can see how in each case we can say how far away is the line at each spot away from its point, and then we can take the average of all those, and that's called the loss. Right? That is the value of our loss. Right? So you need some mathematical function that can basically say how far away is this line from those points. For this kind of problem, which is called a regression problem, a problem where your dependent variable is continuous, so rather than being grizzlies or teddies, it's like some number between -1 and 6. This is called a regression problem. And for regression, the most common loss function is called mean squared error, which pretty much everybody calls MSE. You may also see RMSE, which is root mean squared error. And so the mean squared error is a loss. It's the difference between some prediction that you've made, okay, which is like the value at the line, and the actual number of ice cream sales. And so in the mathematics of this, people normally refer to the actual, they normally call it y, and the prediction, they normally call it y hat, as in they write it like that. Okay. And so what I try to do, like when we're writing something like a mean squared error equation, there's no point writing ice cream here and temperature here, because we want it to apply to anything. So we tend to use these like mathematical placeholders. So the value of mean squared error is simply the difference between those two squared, right? And then we can take the mean. Because remember, that is actually a vector, or what we now call it, a rank 1 tensor. And that is actually a rank 1 tensor. So it's the value of the number of ice cream sales at each place, right? So when we subtract one vector from another vector, and we're going to be learning a lot more about this, but it does something called element-wise arithmetic. In other words, it subtracts each one from each other. And so we end up with a vector of differences. And then if we take the square of that, it squares everything in that vector. And so then we can take the mean of that to find the average square of the differences between the actuals and the predicted. So if you're more comfortable with mathematical notation, what we just wrote there was the sum of, which way around did we do it? Y hat minus y squared over n. Right? So that equation is the same as that equation. So one of the things I'll note here is I don't think this is, more complicated or unwieldy than this, right? But the benefit of this is you can experiment with it. Like once you've defined it, you can use it. You can send things into it and get stuff out of it and see how it works, right? So for me, most of the time I prefer to explain things with code rather than with math, right? Because I can actually, they're the same, right? They're doing, in this case at least, in all the cases we'll look at, they're exactly the same. They're just different notations for the same thing. But one of the notations is executable. It's something that you can experiment with. And one of them is abstract. So that's why I'm generally going to show code. So the good news is if you're a coder with not much of a math background, actually you do have a math background because code is math, right? If you've got more of a math background and less of a code background, then actually a lot of the stuff that you learned from math is going to translate very directly into code. And now you can start to experiment really with your math. Okay, so this is a loss function. This is something that tells us how good our line is. So now we have to kind of come up with what is the line that fits through here. Because remember, we don't know. We're going to pretend we don't know. So what you actually have to do is you have to guess. You actually have to come up with a guess. What are the values of A1 and A2? So let's say we guessed that A1 and A2 are both 1. So this is our tensor. A is 1, 1. Right? So here is how we create that tensor. And I wanted to write it this way because you'll see this all the time. Like written out, it should be 1.0. Oh, sorry, it looks like we're starting with -1. -1. Written out fully, it would be -1.0, 1.0. Like that's written out fully. We can't write it without the point because that's now an int, not a floating point. So that's going to spit the dummy if you try to do calculations with that in neural nets, right? I'm lazy. I'm far too lazy to type .0 every time. Python knows perfectly well that if you add a dot next to any of these numbers, then the whole thing is now floats, right? So that's why you'll often see it written this way, particularly by lazy people like me. Okay, so A is a tensor. You can see its floating point. You see, like even PyTorch is lazy. They just put a dot. They don't bother with a 0, right? But if you want to actually see exactly what it is, you can write dot type, and you can see it's a float tensor. Okay. And so now we can calculate our predictions with this like random guess, x at A, matrix product of x and A. And we can now calculate the mean squared error of our predictions and our actuals, and that's our loss. Okay, so for this regression, our loss is 8.9. And so we can now plot a scatter plot of x against y, and we can plot a scatter plot of x against y hat, our predictions, and there they are. Okay, so this is the 1, comma, minus 1 line, sorry, minus 1, comma, 1 line, and here's our actuals. So that's not great, which is not surprising, because it's just a guess. So SGD, or gradient descent more generally, and anybody who's done engineering or probably computer science at school will have done plenty of this, like Newton's method, whatever. It's all the stuff that you did at university. If you didn't, don't worry, we're going to learn it now. It's basically about taking this guess and trying to make it a little bit better. So how do we make it a little bit better? Well, there's only two numbers, right? And the two numbers are the intercept of that orange line and the gradient of that orange line. So what we're going to do with gradient descent is we're going to simply say, what if we changed those two numbers a little bit? What if we made the intercept a little bit higher or a little bit lower? What if we made the gradient a little bit more positive or a little bit more negative? So there's like 4 possibilities. And then we can just calculate the loss for each of those 4 possibilities and see what worked. Did lifting it up or down make it better? Did tilting it more positive or more negative make it better? And then all we do is we say, okay, well, whichever one of those made it better, that's what we're going to do. And that's it, right? But here's the cool thing, for those of you that remember calculus, you don't actually have to move it up and down and round about. You can actually calculate the derivative. The derivative is the thing that tells you, would moving it up or down make it better, or would rotating it this way or that way make it better? Okay. So the good news is, if you didn't do calculus or you don't remember calculus, I just told you everything you need to know about it, right? Which is that it tells you how changing one thing changes the function, right? That's what the derivative is. Kind of, not quite strictly speaking, but close enough, also called the gradient. Okay, so the gradient or the derivative tells you how changing A1 up or down would change our MSE, how changing A2 up or down would change our MSE, and it just does it more quickly. It does it more quickly than actually moving it up and down, right? So in school, unfortunately, they forced us to sit there and calculate these derivatives by hand. We have computers. Computers can do that for us. We are not going to calculate them by hand. Instead, we're going to call .grad. On our computer, that will calculate the gradient for us. So here's what we're going to do. We're going to create a loop. We're going to loop through 100 times, and we're going to call a function called update. That function is going to calculate y hat, our prediction. It is going to calculate loss, our mean squared error. From time to time, it will print that out so we can see how we're going. It will then calculate the gradient. And in PyTorch, calculating the gradient is done by using a method called backward. So you'll see something really interesting, which is mean squared error was just a simple standard mathematical function. PyTorch, for us, keeps track of how it was calculated and lets us calculate the derivative. So if you do a mathematical operation on a tensor in PyTorch, you can call backward to calculate the derivative. What happens to that derivative? It gets stuck inside an attribute called .grad. So I'm going to take my coefficients A, and I am going to subtract from them my gradient. And there's an underscore here. Why? Because that's going to do it in place. So it's going to actually update those coefficients A to subtract the gradients from them, right? So why do we subtract? Well, because the gradient tells us if I move the whole thing downwards, the loss goes up. If I move the whole thing upwards, the loss goes down. So I want to do the opposite of the thing that makes it go up, right? So because we want our loss to be small. So that's why we have to subtract. And then there's something here called LR. LR is our learning rate. And so literally all it is the thing that we multiply by the gradient. Why is there any LR at all? Let me show you why. Let's take a really simple example. A quadratic. Right? And let's say your algorithm's job was to find where that quadratic was at its lowest point. And so how could it do this? Well, just like what we're doing now, the starting point would just be to pick some x value at random. And then pop up here to find out what the value of y is. Okay? And that's its starting point. And so then it can calculate the gradient. And the gradient is simply the slope. Right? It tells you moving in which direction is going to make you go down. And so the gradient tells you you have to go this way. So if the gradient was really big, you might jump this way a very long way. So you might jump all the way over to here, maybe even here, right? And so if you jumped over to there, then that's actually not going to be very helpful, because then you see, well, where does that take us to? Oh, it's now worse, right? We jumped too far. So we don't want to jump too far, so maybe we should just jump a little bit, maybe to here. And the good news is that is actually a little bit closer. And so then we'll just do another little jump, see what the gradient is, and do another little jump. That takes us to here. And another little jump. That takes us to here. 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 Right? So in other words, we find our gradient to tell us kind of what direction to go and do we have to go a long way or not too far. But then we multiply it by some number less than 1 so we don't jump too far. And so hopefully at this point, this might be reminding you of something, which is what happened when our learning rate was too high. So do you see why that happened now? Our learning rate was too high, meant that we jumped all the way past the right answer, further than we started with, and it got worse and worse and worse. So that's what a learning rate too high does. On the other hand, if our learning rate is too low, then you just take tiny little steps. And so eventually you're going to get there, but you're doing lots and lots of calculations along the way. So you really want to find something where it's kind of either like this, or maybe it's kind of a little bit backwards and forwards. Maybe it's kind of like this. Something like that. You know, you want something that kind of gets in there quickly, but not so quickly it jumps out and diverges, not so slowly that it takes lots of steps. So that's why we need a good learning rate. And so that's all it does. So if you look inside the source code of any deep learning library, you'll find this. You'll find something that just says coefficients.subtract learning rate times gradient. And we'll learn about some we'll learn about some easy but important optimizations we can do to make this go faster. But that's basically it. There's a couple of other little minor issues that we don't need to talk about now, one involving zeroing out the gradients, another involving making sure that you turn gradient calculation off when you do the SGD update. If you're interested, we can discuss them on the forum. Or you can do our Introduction to Machine Learning course, which covers all the mechanics of this in more detail. But this is the basic idea. So if we run update 100 times, printing out the loss from time to time, you can see it starts at 8.9, and it goes down, 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 down. And so we can then print our scatter plots, and there it is. That's it. Believe it or not, that's gradient descent. So we just need to start with a function that's a bit more complex than x at a. But as long as we have a function that can represent things like, is this a teddy bear, we now have a way to fit it. Okay? And so let's now take a look at this as a picture, as an animation. And this is one of the nice things that you can do with Matplotlib, is you can take any plot and turn it into an animation, right? And so you can now actually see it updating each step. So let's see what we did here. We simply said, as before, create a scatter plot. But then rather than having a loop, we used Matplotlib's func animation to call 100 times this function. And this function just called that update that we created earlier, and then updated the y data in our line. And so it did that 100 times, waiting 20 milliseconds after each one, and there it is, right? So you might think that like visualizing your algorithms with animations is some amazing and complex thing to do, but actually now you know it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 lines of code. Okay, so I think that is pretty damn cool. So that is SGD visualized. And so we can't visualize as conveniently what updating 50 million parameters in a ResNet 34 looks like, but it's basically doing the same thing. Okay, and so studying these simple versions is actually a great way to get an intuition. So you should try running this notebook with a really big learning rate, with a really small learning rate, and see what this animation looks like. Right, and try and get a feel for it. Maybe you can even try a 3D plot. I haven't tried that yet, but I'm sure it would work fine too. So the only difference between stochastic gradient descent and this is something called mini batches. You'll see what we did here was we calculated the value of the loss on the whole data set on every iteration. But if your data set is 1.5 million images in ImageNet, that's going to be really slow, right? Just to do a single update of your parameters, you've got to calculate the loss on 1.5 million images. You wouldn't want to do that. So what we do is we grab 64 images or so at a time at random, and we calculate the loss on those 64 images, and we update our weights. And then we grab another 64 random images, and we update the weights. So in other words, the loop basically looks exactly the same, but at this point here, it would basically be y, square bracket, and some random indexes here, and some random indexes here, and would basically do the same thing. Well, actually, sorry, it would be there, right? So some random indexes on our x and some random indexes on our y to do a mini batch at a time. That would be the basic difference. And so once you add those, grab a random few points each time. Those random few points are called your mini batch, and that approach is called SGD, or stochastic gradient descent. Okay. So there's quite a bit of vocab we've just covered, right? So let's just remind ourselves. The learning rate is a thing that we multiply our gradient by to decide how much to update the weights by. An epoch is one complete run through all of our data points, or all of our images. So for the non-stochastic gradient descent we just did, every single loop we did the entire data set. But if you've got a data set with 1,000 images and your mini batch size is 100, then it would take you 10 iterations to see every image once. So that would be one epoch. Epochs are important because if you do lots of epochs, then you're looking at your images lots of times. And so every time you see an image, there's a bigger chance of overfitting. So we generally don't want to do too many epochs. A mini batch is just a random bunch of points that you use to update your weights. SGD is just gradient descent using mini batches. Architecture and model kind of mean the same thing. In this case, our architecture is y equals xa. Right? The architecture is the mathematical function that you're fitting the parameters to. And we're going to learn either today or next week what the mathematical function of things like ResNet 34 actually is. But it's basically pretty much what you've just seen. It's a bunch of matrix products. Parameters, also known as coefficients, also known as weights, are the numbers that you're updating. And then loss function is the thing that's telling you how far away or how close you are to the correct answer. Any questions? All right, so these models, these predictors, these teddy bear classifiers are functions that take pixel values and return probabilities. They start with some functional form, like y equals xa, and they fit the parameters a using SGD to try and do the best to calculate your predictions. So far we've learned how to do regression, which is a single number. Next week we'll learn how to do the same thing for classification, where we have multiple numbers, but it's basically the same. In the process, we had to do some math. We had to do some linear algebra, and we had to do some calculus. And a lot of people get a bit scared at that point and tell us, I am not a math person. If that is you, that's totally okay, but you're wrong. You are a math person. In fact, it turns out that when in the actual academic research around this, there are not math people and non-math people. It turns out to be entirely a result of culture and expectations. So you should check out Rachel's talk. There's no such thing as not a math person, where she will introduce you to some of that academic research. And so if you think of yourself as not a math person, you should watch this so that you learn that you're wrong, that your thoughts are actually there because somebody has told you you're not a math person. But there's actually no academic research to suggest that there is such a thing. In fact, there are some cultures, like Romania and China, where the not a math person concept never even appeared. It's almost unheard of in some cultures for somebody to say, I'm not a math person, because that just never entered that cultural identity. So don't freak out if words like derivative and gradient and matrix product are things that you're kind of scared of. It's something you can learn. It's something you'll be okay with. Okay? So the last thing that we're going to close with today. Oh, I just got a message from Simon Willison. Simon's telling me he's actually not that special. Lots of people won medals. So that's the worst part about Simon, is not only is he really smart, he's also really modest, which I think is just awful. I mean, if you're going to be that smart, at least be a horrible human being and, you know, make it okay. Okay, so the last thing I want to close with is the idea of, and we're going to look at this more next week, underfitting and overfitting. We just fit a line to our data. But imagine that our data wasn't actually line-shaped, right? And so if we tried to fit something which was like constant plus constant times x, i.e. a line to it, then it's never going to fit very well, right? No matter how much we change these two coefficients, it's never going to get really close. On the other hand, we could fit some much bigger equation. So in this case, it's a higher degree polynomial with lots of wiggly bits, like so, right? But if we did that, it's very unlikely we go and look at some other place to find out the temperature that it is and how much ice cream they're selling and that we'll get a good result, because like the wiggles are far too wiggly. So this is called overfitting. We're looking for some mathematical function that fits just right, to stay with the teddy bear analogies. So you might think, if you have a statistics background, the way to make things fit just right is to have exactly the right number of parameters. It's to use a mathematical function that doesn't have too many parameters in it. It turns out that's actually completely not the right way to think about it. There are other ways to make sure that we don't overfit. And in general, this is called regularization. Regularization are all the techniques to make sure that when we train our model, that it's going to work not only well on the data it's seen, but on the data it hasn't seen yet. So the most important thing to know when you've trained a model is actually how well does it work on data that it hasn't been trained with. And so as we're going to learn a lot about next week, that's why we have this thing called a validation set. So what happens with a validation set is that we do our mini batch STD training loop with one set of data, with one set of teddy bears, grizzlies, black bears. And then when we're done, we check the loss function and the accuracy to see how good is it on a bunch of images which were not included in the training. And so if we do that, then if we have something which is too wiggly, it'll tell us, oh, your loss function and your error is really bad, because on the bears that it hasn't been trained with, the wiggly bits are in the wrong spot. Or if it was underfitting, it would also tell us that your validation set's really bad. So, like, even for people that don't go through this course and don't learn about the details of deep learning, like if you've got managers or colleagues or whatever at work who are kind of wanting to like learn about AI, the only thing that you really need to be teaching them is about the idea of a validation set, because that's the thing they can then use to figure out, you know, is somebody selling them snake oil or not? You know, to like hold back some data, and then they get told like, oh, here's a model that we're going to roll out. And then you say, okay, fine. I'm just going to check it on this held out data to see whether it generalizes. There's a lot of details to get right when you design your validation set. We will talk about them briefly next week, but a more full version would be in Rachel's piece on the FastAI blog called How and Why to Create a Good Validation Set. And this is also one of the things we go into in a lot of detail in the Intro to Machine Learning course. So we're going to try and give you enough to get by for this course, but it is certainly something that's worth deeper study as well. Any questions or comments before we wrap up? Okay, good. All right, well, thanks everybody. I hope you have a great time building your web applications. See you next week.